All right, so last time we finished off by starting to talk about auxiliary equations. So again, these are equations of constraints. So in this case, we're specifically looking at algebraic constraints. Again, we have some sort of algebraic expression, which is this equation here we're calling G. Again, is going to be equal to 0. So as we talked about in class, when we talk about the geodesic, we're simply saying that the radius must be constant at all times. So you have x squared plus y squared plus z squared must be equal to the radius squared, or in this case, subtract the radius squared. So that then gives you the x squared plus y squared plus z squared minus r squared is equal to 0. So that's our equation of G. So in general, these guys have to be dealt with. Now, there's of course all kinds of different ways we can deal with them, but let's just put them into the equation uh, and talk about how it actually goes more in general. And then again, there's other ways where you can actually just replace one variable with another one as long as you have an algebraic constraint. But in this case, let's look at the more general way of actually doing it. So let's say that our integrand depends on both y, or let's say two variables, right? So let's say y and z. So in this case, I'm going to write MIF, which is yi prime with x. Actually, it only depends on two variables. Say that this is going to be f y prime as well as z prime, and then possibly on x as well. So in this case, saying y1 is equal to simply y, and then y2 is equal to z. Okay. So now, what do we know? So we know if we were going to take our integral, which is our functional integral, so we're going to integrate this guy from f1 to, or sorry, x1 to x2, dx of then f of, that's right, this says y prime, z prime, x. And again, we want to vary this guy. So again, we want to take the partial derivative of this with respect to alpha by varying the two in exactly the same ways we did before, and then write this in terms of partial derivatives. Skip all these steps because we've seen all of them a couple times so far. But what we get is then, so now we get the partial of f with respect to y minus then ddx by our integration by parts of the partial of f with respect to y prime. And all then times the partial of y with respect to alpha. Now we're going to get plus, same thing for now z. So I'm going to take the partial of f with respect to z minus then the full derivative with respect to x of the partial of f with respect to z prime, all then times partial of z with respect to alpha. Okay. Now, here, this is where we have to add our constraints. Sorry, whoops, subtract all that stuff there. There we go. Plus. Good. So this is where we have to add our constraints. Our constraint equation now is going to be the same thing as, but y and z, which depend on possibly x, is then equal to 0. Now, by using this guy, what we can see then is what? So unlike before, our partial derivative, for example, of y with respect to alpha and our partial derivative of z with respect to alpha are no longer independent because they're forced to be coupled with each other by our expression of g, or our constraints. So these guys are no longer independent, but they're actually dependent functions. So we basically have to take this into account, which basically means that I keep erasing all this. Anyways, the point is that since these guys are now coupled, that means that these expressions here are no longer independent of each other, which means that this thing can depend on z, this one can depend on y, which means that these two things here cannot separately go to 0 anymore, unlike they did when we had simply two variables. So what we're going to have to do in this case then is basically try to uncouple them by using our constraint equation. And the way that we're going to do that is let's take the derivative of g. So it's going to be the same thing then as the partial of g with respect to alpha, d alpha, then is going to be equal to the partial of g with respect to y times the partial of y with respect to alpha, plus then the partial of g with respect to z times the partial of z with respect to alpha, all then times d alpha. And all this has to be equal to 0 because the original g function was equal to 0. Now, notice that here, first of all, that the partial of x with respect to alpha is equal to 0 because there's nothing here that actually depends on that. So now let's look at each one of these guys. So now what we know is that, again, we have yi x of alpha is then equal to yi x 0 plus then eta I, which depends on x times alpha. There we go. So basically, what this means then is what? If I wrote this in terms of each one, so in this case, I get a y of x alpha is then equal to y of x 0 plus alpha eta, which depends on y, x. Then we get a z x alpha, then equal to, sorry, z x 0 plus alpha eta z, which depends on x. Right? So again, this is just our reparameterization of our paths that we're varying over alpha. So now if we look at the partial derivatives of each one of these, so notice that partial of y with respect to alpha is then just going to be eta of y, and then a partial of z with respect to alpha is then going to be eta z. So now let's put those both into our expression from above. So basically this expression. So let's plug those into there. So now we're going to get then is the partial of g with respect to y times then eta y plus the partial of g with respect to z times then eta z then must be equal to 0. Now, since this is 0, what that's going to know to do is now isolate each one of these two pieces. So finally, we're going to get then the partial of g with respect to y times eta y must then be equal to negative the partial of g with respect to z times then eta z. Mhm. Now, what this is ultimately going to do is it's going to give me a relationship then between the etas, which I can now use into our variable above, because now what we did originally when we did all this is we used the fact that the etas were the same, and we had to have the fact that what the etas were arbitrary, so that each one of those terms had to go to 0 separately. But ultimately, what this is going to allow me to do then is separate this into now one eta, where I can now pull out the eta to then allow me to then set everything on the inside then equal to 0. So let's talk about how that's going to work. So let's solve this as a ratio of the eta. So I'm going to get eta z divided by eta y, then it's going to be equal then to minus partial of g with respect to y divided by the partial of g with respect to z. Now, let's plug that back into our variation of j. So we're going to get partial derivative of j with respect to alpha, the integral from x1 to x2, dx. So let's plug that guy in. So I'm going to get what? The partial of f with respect to y. And then I'm going to get a minus full derivative with respect to y prime. One. And then from above, we know that this is going to be the partial of what? Y with respect to alpha, but that's going to be the same thing as eta y. All right. And I get my plus then the partial of f with respect to z minus the full derivative of then the partial of f with respect to z, all then times eta z, all then integrated over again dx. Now, again, using our relationship here, what we can do then is replace the z here, the eta z, with now eta alpha, by then saying that eta z then is equal to minus the partial of g with respect to y divided by the partial of g with respect to z, all then times eta y. So now both terms will only depend on eta y, which we can then pull outside of the integral. And again, then we can say, since this thing here is equal to 0, again, all this is only proportional to eta y, and eta y must be a arbitrary function. Then we can set the integrand then equal to 0 like we did last time. So let's go ahead and do that. So it's going to be the integral from x1 to x2 dx of, I'm going to get the partial of f with respect to y minus the full derivative the partial of f with respect to y prime. I'm going to pull out the eta, and then I'm going to get a minus the partial of f with respect to z, minus then d dx, then the partial of f with respect to z. Then that whole thing's going to be multiplied then by that partial of g with respect to y divided by the partial of g with respect to z, all then times a to y. Now, again, since a to y here must be an arbitrary function, what that means then is that the entire integrand here must be equal to 0. Now, the beautiful part about this is now we can now cross multiply since this whole thing is equal to 0, which now allows me to separate the two terms. So let's see how that works. Let's go ahead and do that. So now my integrand, write all that out, and then going to get, that's what, partial of f, partial of y minus then d dx, of then the partial of f with respect to y prime must then be equal to plus the partial of f with respect to z minus then the full derivative of the partial of f with respect to z prime, all then times, and the partial of g with respect to y divided by the partial of g with respect to z. So now I can bring all the y terms to one side, all the z terms to one side, which means that I'm now fully decoupling my expression to have one on one side, one on the other side. So let's write that. So finally, what I get is the partial of f with respect to y minus then d dx, or the partial of f with respect to y prime, all multiplied then by partial of g with respect to y inverted, then equals to the partial of f with respect to z minus then dx, partial of f with respect to z prime, all then times the partial of g with respect to z, again, inverted. Now, again, what this means then is that everything on this side only depends on y, everything on this side only depends on z, which means now we've fully decoupled everything. Now, if the left-hand side only depends on y, and the right-hand side only depends on z, and they're equal to each other, that means that each one of these two terms separately must be equal to a constant. Beautiful. That's all this thing means. So these guys basically are just separable. They have to equal some sort of constant, and that constant we're just going to call negative x, or sorry, negative lambda, where lambda can be a function of x because, as we pointed out earlier, nothing here actually depends on x. So we can't have anything to say about x. All we know then is that what the y portion must be 0, but it can still depend on x. So ultimately what this says then is for each one of these guys, we're going to get the partial of f to I minus then dx of the partial of f with respect to y prime, all times r partial of g over partial of y minus 1 must be equal to some constant lambda x. Right? Now, since I only have the two terms, that means this is equal to, again, minus lambda x, where this guy is also then equal to minus lambda x. So they have to equal the same constant. So we're going to get a similar expression for the z, and for z. So from here, I can now what? Multiply both sides by this guy, then set equal to 0. This is going to be our new Lagrange equation we have to determine. So finally, at the end of the day, what I get then is the partial of f with respect to y minus then d dx of the partial of f with respect to y prime plus lambda, which depends on x, times the partial of g with respect to y must equal 0. Simultaneously, exactly the same expression for z, but now we're just replacing y with z. So the beautiful part is, again, this thing separates into two equations, in this case, which are independent of each other. But now they depend on this extra term, which is our Lagrange multipliers. Our Lagrange multipliers, which hopefully you remember from Calc 3. If not, that's okay. Lagrange multipliers. There we go. So basically now I just have a modified expression that I have to solve. So in this case, I have three independent variables, right? I have lambda, I have what? I also have y and I have z, but we also have three equations because we have the equation for lambda itself which means that what? We have three equations, we have three unknowns, so we can actually solve this. Now, when we start talking about this in the future, when we put it specifically into mechanics, this thing will also tell us other things about forces, which we'll talk more about later, but these lead to what are called constraint forces. So things like, or actually what we also call generalized forces, which lead to things like normal forces and et cetera. So this actually just tells me how my system is constrained. So yeah, so anytime I have an algebraic expression, in this case, my Lagrange equation simply becomes this guy. Or in a more general sense, so if I had I is equal to 1, 2, all the way out to n variables, what happens in that case then is this thing actually just generalizes to the fact that the partial of f with respect to I minus then the full derivative of then the partial of f with respect to yi prime. Then I'm going to get plus sum over j of then lambda jx times then the partial of gj, then divided by the partial of yi, must then be equal to 0, where in this case we have g of I j j excuse me, x must then be equal to 0. So in this case, j just then represents the total number of constraint equations that I actually have. So in this case, if we have I then goes out from, again, 1, 2, all the way out to n, then we might have a number of constraint equations, which are then out to some other variable m, where m does not have to equal n. Typically, it's going to be a little less than n. Like in this problem, we had 2, so I was 1 and 2, and j was 1. We had one constraint equation. So in this equation, at the end of the day, we're going to have what? M plus n total number of equations. Which means in this case, we're going to have also m plus n total variables. So then we can solve a system of n plus m equations, depending on the size of it. So again, this is when we have algebraic. We can also have other types of constraint equations. We'll talk more about those, but the first one we can have is actually, we can have differential constraints. So differential constraint equations, or auxiliary equations. Equations. These are very similar, but now what happens then is that I have differential equations, which now constrain my system instead of algebraic expressions. So in this case, we may have a set of, I don't know, m number of differential equations. So in this case, we're going to take j then runs from 1 out to m. So that now our constraint equations become the sum over j again of the partial of gj with respect to yi dyi is equal to 0. So these are now my differential equations that are now my constraint equations, which again, we'd have to put into our system. But let's do an example of an algebraic one. So let's say I have something I've talked about several times, but let's say I have a object which is rolling without slipping. So in this case, we have an angular velocity, right, going around this way. We also have a center of mass velocity. And what we also know is as this thing rolls, let's say it rolls from this position then to this position here, so that the center of mass location moves by an amount, we call that y. What happens in this case then is this point here will then rotate to another point here, so that it undergoes this arc length across here. So this is s. Now, in this case, since it's rolling without slipping, what that means then is, as we know from physics 205, y then must be equal to s, which means that the arc length that the wheel rolls through has to be equal to the same linear distance at which the object, wheel, or whatever it is rolls. Means that using arc length, this is then going to be the same thing as r times theta. So in this case, our constraint equation g then equal to simply y minus r theta. Okay? So this is then my coordinates, which it is that I'm going to use. We'll talk more about these later. These are called generalized coordinates, but that's fine. So in this case, it wants us to simply determine the constraint equation and then determine the partial derivative. So again, this is my constraint equation. So this is my g, which depends on y and theta, and is equal to y minus r theta, that is equal to 0. So in this case, let's look at our partial derivatives. So I'd have the partial derivative of g with respect to y, then is simply 1, and then the partial of g with respect to theta then is equal to negative r. Nice easy example. So in this case, this would be my constraint equation, and then these would be the factors which get multiplied by my Lagrange multipliers, and then I would just have to determine my Lagrange multipliers from there. So the last type of constraints I'm going to talk about is an integral constraint. We can also have integral constraints, so we can have algebraic constraints, differential constraints, and now we can have integral constraints as well. So an integral constraint is one where, say we have our integral, which is also a functional. So in this case, it's a functional integral because it depends on, again, y. Let me write that slightly differently. So let's say this is my constraint equation, k, which is then going to be equal then to the integral, let's say from x1 to x2 of g now, which depends on y, y prime, x, and I'm going to integrate this guy over dx. Now, just like we saw in the algebraic one introduced a Lagrange multiplier. So what we should assume then is that the integral one should also introduce a Lagrange multiplier, which in this case is some sort of constant, which we can then plug into our expression. Right, so now, adding in our constraints, our equation j, which is our functional integral, now is going to become j plus k, which is now going to be equal then to the integral. I'm sorry, not plus k, but plus some Lagrange multiplier times k. There we go. So this is going to be equal then to the integral from, again, x1 to x2, integrated over dx, then of, in this case, f plus lambda g, all integrated over dx. Now again, if I do my variations that I've done, i.e. the partial derivative of j with respect to alpha, and then eventually set that guy equal to 0, by repeating all that process, I'll skip all the steps, but basically we find is that the partial of f with respect to y minus then the full derivative, there we go, the partial of f with respect to y prime, plus lambda times the partial of g with respect to y minus then d dx, the full derivative of the partial of g with respect to y prime, all then must be equal to 0. So again, notice this thing here is basically the Lagrange, or the Euler equation, sorry, the Euler equation. And now for g instead of y, right? But again, has exactly the same structure. And again, that just becomes of the variation. Pardon me. So this guy typically is going to satisfy some sort of boundary conditions. So on top of this, we'll have some sort of boundary conditions. Or the boundary conditions then is our function has to satisfy some particular constants at the boundary, which means that, for example, y of x1 has to equal some constant a, then y at a second boundary x2 has to equal some other constant b. And this may represent something like a length of something, right? So for example, if I had a length of a wire, which was bounded to have some length of L, overall, this is my point A, and this is my point B, then I have to constrain the length of this wire or string or cord or whatever it is by the length of him. So this is typically where this type of constraint equation will come from. And this is what's called a isoparametric constraint or in an isoparametric problem. So this is where this type of constraint usually shows up from. So beautiful. So let's use this. Let's do an example. So let's say we want to find the curve y of x of length L bounded by the x-axis on the bottom that passes through the points negative a and positive a along the x-axis, and then 0 in the y direction, and encloses the largest amount of area. So this is what's known as the Dido problem. So this is our example. So in this case, again, let's say here's my y-axis, here's my x-axis. So I have this point here, which is minus a. I have this point here, which is a. And then I have some length of string. So here's my string length L. And in this case, we want to know how should I bend the string so that I have the maximum amount of area. So basically meaning, should I bend my string something like this? So that in this case, I get the maximum amount of area here, or should I do something else, right? Should I make some other type of shape, maybe a triangle, for example, right? Something that kind of looks like this. Is that going to give me the greatest amount of area? Right. So basically, we just want to know what shape is going to give the maximum amount of area in this case. So good. So let's talk about this guy. So let's say, go back to my original shape here. Draw that one in black now. So here's my original shape. So in this case, let's look at the differential area. So in this case, I'm going to cut out a small little tiny section like this. Now my wedge that I'm going to cut out. So this thing then is going to have a thickness. This is my x-axis here. Right? And this is going to have a thickness then of dx, and it's going to be at some particular y height. Let me do that in red, which is then the y height here. Right? So then the area of the strip, dA, then is going to be simply y times dx. So in this case, what we want to maximize is our area. Right? So great. So in this case, we have the area then going to be equal to the integral of the differential area, which is then equal to, in this case, the integral over dx from, in this case, minus a to positive a integrated by y, right? Now, this is the differential area. However, and we want the fact that the length of the string is equal to a constant, so we're going to introduce our straight equation, k, which is that the integral over the length of the string, which in this case is my differential length here, I'm going to call that guy simply ds, must then be equal to a constant, which in this case is L, right? So if I chop this thing up into a whole bunch of small pieces, and then I integrate by summing all those pieces together, it has to be a fixed constant, which is this guy. Now in this case, our other thing we have to pay attention to is, again, in the y direction, the endpoints must be at 0, which means that y of negative a must be equal to y of a, which must be to 0. Those are boundary conditions. Now, since I'm integrating over the length of this guy, we know then is that what ds is going to be the same thing then as what the square root dx squared plus then dy squared. And again, x is our independent parameter, so it's going to be then dx times the square root of 1 plus y prime squared. Same thing we've seen like 1,000 times now. Good. So this is going to be the same thing as the integral from minus a to a dx of the square root of 1 plus y prime squared. And again, we want this guy to simply be equal to L at the end of the day. Oh, God. So good. So let's look at each one of these. So we know this is the one that we originally want. So this is our j. So j is equal to the integral, again, of f dx. So looking at this guy, this means that f then is simply equal to y. Then this is our integral of g integrated over dx, which means g then is going to be equal to the square root of 1 plus y prime squared. So these are my two different equations. So that's my f and that's my y. So let's go ahead and plug these into our constraint equation we wrote above, right? So now what we have is the partial of f with respect to y minus then d dx of the partial of f with respect to y prime, plus then, where was I? Lambda, right? Times then the partial of g with respect to y, good, minus then the full derivative of the partial of g with respect to y prime, and all that then has to be equal to 12, right? So the equation that we wrote down above. Good. Now, let's do that. So again, we know f is simply equal to y, which means the partial of f with respect to y is equal to 1, but the partial of f with respect to y prime is equal to 0, right? Simultaneously, we also know that for g, in blue, we have the partial of g with respect to y is equal to 0 because g has no y dependence. And then a partial of g with respect to y prime is going to be then 1/2 2 times y prime, all divided by the square root of 1 plus y prime squared. That my 2's here are going to cancel. So let's plug that in. So what I get then is 1 minus 0 plus lambda times 0 minus d dx of then y prime all over the square root of 1 plus y prime squared equals 0. So from here, let's go ahead and solve this guy. So all I'm going to do then is bring this term over here. So I'm going to divide the whole thing by lambda and bring the other term to the other side. So finally what I get then is that d dx of then y prime over the square root of 1 plus y prime squared must then be equal to 1 over lambda. So good. So let's go ahead and integrate both sides of this. So I'm going to integrate this side with respect to x, integrate this side with respect to x, and then go ahead and solve. Let's do that. So all I get in this case then is the right-hand side is just going to give me an x. So, and the left-hand side is going to give me, let's write all this out. So in this case, notice I'm taking a derivative of all this and I'm integrating over that, which means I'm just going to get the same thing back. So at the end of the day, I'm going to get y prime divided by the square root of 1 plus y prime squared is equal to 1 over lambda times x minus some constant, my integration constant, which I'm going to call c1. I'm only taking it as negative because of convenience, and you're going to see that in a second. But again, C1 here is just some sort of integration constant. Beautiful. So what? Let's keep working on this. Let's go ahead and solve this guy. So first things first, we got to solve this guy for y prime. So let's go ahead and do that. So all we're going to do then is let me move the lambda to the other side, just make it a little bit easier. So I'm going to multiply both sides by the square root and then square both sides. Let's do that. So now we're going to get then is that what lambda squared times y prime squared is then equal to 1 plus y prime squared times x minus c1 squared. Fantastic. And then we're going to solve that guy. So all I'm going to do then is what? Subtract the one term over to the other side and then divide lambda squared minus then x minus c1 squared all times lambda, sorry, y prime squared is then equal to x minus c1 squared. Now let's divide and take a square root. So at the end of the day, we're going to get that y prime, which is dy dx, is equal to x minus c1, sorry, I'm trying not to sneeze, square root of lambda squared minus x minus c1 squared. Good. Now, from here, since I want y, let's integrate this guy. Easiest way to do this is integration with a u substitution, but I'm not going to bother doing all that. I'll just kind of write down what the answer is. But here you would just use a u sub. Do that integral, but you're just going to get that what dy integral is equal to y is then going to be equal then to the integral over dx of then x minus c1 all divided by the square root of y squared minus x minus c1 squared. Excuse me. So integrating this guy, what we find then is, again, here I'm just going to use a u sub, but this turns out then to be the square root of lambda squared minus x minus c1 squared plus some other c2, where this is my second integration constant because we're doing two integrals at the end of the day. This is our second integration constant. Now these integrated constants we're going to get rid of by using our boundary conditions here in a second. But ultimately, if I find this guy, or if I solve this guy now for lambda squared, then I'm going to subtract the c2, square that, and then add the two terms the other side. But at the end of the day, what we get then is that lambda squared then is equal to x minus c1 squared plus y minus c2 squared, which is actually just a circle. This is the equation of a circle. ultimately, what this thing says then is what? The shape that gives me the greatest amount of area when I'm fixing my function is what? Just a circle, where the radius of that circle then is going to be lambda, and this guy's going to be centered at the point of C1, E2. Right? Now, in this case, of course, using our boundary conditions, where this is then minus a and this is positive a, we can easily find the fact that C1 is equal to C2, which is equal to 0, which basically, or not, 0 should be a. Sorry, my bad. So anyways, so yeah, no, 0. I was right the first time. So this thing is bounded by the fact that it has to be at the origin. Good. So in this case, we have that simply lambda squared, that is going to be x squared plus y squared, which again is just going to be our equation of a circle. So this is my, again, x-axis, this is my y-axis. Again, if this is negative a, and then this is positive a, again, the shape that maximizes the area for a fixed length of string is then going to be simply that of a circle, which has the radius of lambda. Right? And then finally, we can also find out what lambda is by the fact that what we know the length of the string has to then be equal to what? By arc length pi times a, which means that what a then must be equal then to pi divided by the length of the string. So in this case, we can determine exactly what lambda is, where in this case, we actually didn't have to use that. Lambda has to be equal to a because it has a radius of simply a. So good. So that's an example of an integral constraint equation. Last thing I want to talk about real quick is what we call delta notation. So typically when you look in most textbooks or you look in papers or things like this, they actually don't determine the Euler equation by using this notation. So they don't look at partial of j with respect to alpha and set this guy equal to 0. What they do instead is they use this thing which is called delta notation. So delta notation is basically the same idea. So we're going to start off with our j with respect to alpha is then equal to the integral, again, from x1 to x2, then the partial of f with respect to y, minus the full derivative with respect to x, the partial of f with respect to y prime. And then in this case, they're going to, again, get their eta, and then we're going to integrate over dx, right? Now, typically, the delta notation is a simpler way of writing this in the fact that what I do is multiply both sides then by the alpha, which then we're going to define then this thing to be simply the variation of j. So what we call delta j. Okay? So this delta j here is what's known typically as the variation of j, or the variation of the function of j. So basically, again, it's the same thing, except instead of thinking about it as reparameterizing your path in respect to alpha, all you're basically saying is if I vary j itself over the path of y, so I'm letting y kind of vary, I'm looking at the variation of how it changes. And again, what we want to do is we want to set this guy equal to 0. So you're just looking at varying the original integral and then setting that guy equal to 0. So ultimately, the way we end up typically writing this is that the variation of j equal to the integral from x1 to x2. Everything on the inside stays the same. Control f with respect to y prime. But now we don't get an eta, we get just simply the variation of the path y times then dx, where in this case, we're basically just identifying then that the, excuse me, the variation is the same thing as the partial of y with respect to alpha times then the alpha. Right? So this is what we call the variation. So ultimately what's happening is you're still taking the partial derivative of y with respect to alpha, but then you're multiplying by the differential change of alpha, which is basically just called the variation of path. Right? So again, it's a slightly different way of doing the same thing, but ultimately, again, you're thinking about it in just varying the path itself instead of reparameterizing the path. So basically, the condition for extremum in this case, so my condition it becomes that the variation of j has to be equal to 0, which is going to be then equal to the variation of the integral of f integrated over dx, which is going to be the same thing then as, because the variation is independent of the integral, this is then going to be the integral of the variation of the function f with respect to x from x1 to x2. So again, all we're doing is we're varying the inside, which again, basically works exactly the same way. So if I wrote this out, this would be the integral from x1 to x2 of then the partial derivative of f with respect to y times the variation of y plus the partial of f with respect to y prime times then the variation of y prime times then dx, right? So in this case, I'm varying y prime. So what does that thing mean? So the variation of y prime is the same thing then as the variation of the derivative of y with respect to x, right? Now, in this case, what we're doing then is we're assuming that we can bring the variation on the inside, right? So instead of looking at the variation of the derivative, we're going to look at the derivative of the variation. Now, what we're assuming then is, again, at the endpoints are fixed so that when we vary it at the endpoints, we can't vary the points, which means that the derivative has to be fixed at the endpoints because in this case, again, at our endpoints, the derivative must then be equal to 0 at the endpoints, right? So this is what's known as Dirichlet boundary conditions, right? So in this case, this guy then is going to become equal to the derivative of the variation of y, right? Now, the usefulness of this is now this equation here, carry that down over here, so it doesn't become confusing, becomes x1, x2, and the partial derivative of f with respect to y, variation of y, plus the partial of f with respect to y prime times then the derivative of the variation of y. So this is very similar to where we had before when we looked at the general case with alpha. So now all we want to do is to get the variation of y outside, we now have to transfer this derivative from this term to this term. And as we talked about before, that's done by integration by parts. This guy becomes equal to the integral from x1 to x2, and then the partial of f with respect to y, minus from the integration by parts ddx of partial of f with respect to y prime. And now since every term is multiplied by partial of y, we pull that guy out. This becomes dx. And again, since the variation here must be arbitrary, then in this case, it can't be 0. So when this thing is ultimately equal to 0, that means, again, the integrand has to be to 0, which again gives me the Euler equation. So again, ultimately, again, it's exactly the same thing. The difference is this is actually what's known as virtual work. So the difference between the two is that one uses what's called virtual work. What virtual work basically means is you're holding everything fixed, but then you're looking at the work that's done over then a virtual displacement. So basically meaning that if this was your path, then we're going to vary the path by a small amount here so that it becomes this path now. And where this small amount then is our delta y, right? So this is then our original path. Our original path is y, and now we're moving it by that amount. So now we have varied the path to now this path here. So this is our new path. So y is now our new path. Now we're doing this in a weird way in the fact that the work is equal to 0. So in this case, the work is equal to 0, which is why it's known as virtual work. So you're doing this in a way that you are instantaneously moving it. So you're not doing it over time, which means that the time derivative is simply equal to 0. So I'm moving this in a small amount, but at the same moment of time. So it's done instantaneously. So it's an instantaneous change. Yes, change. So this is what it technically means by the variation of path. So again, called virtual work. Again, it's a typical way that you'll see it written in like higher level textbooks or in most papers where they're thinking about it this way. But ultimately, it's the same process as reparameterizing the path and then varying the path by the parameterization by varying the function of alpha. It's just a different conceptual way of actually doing it. But so again, difference between, again, reparameterizing, so just saying that I have all these different multiple paths where each one of these depends on a different alpha, but the endpoints must be fixed, or thinking about I'm moving from one path to another path by a small amount of dy, and then I'm looking for which one of these paths allows it to be the largest by these small little variations. But again, the time difference between the two is then equal to zero, because again, it's just what we call virtual work. But again, whichever way you want to think about it, it doesn't really matter. It gives you exactly the same expression at the end of the day, which is then simply the Euler equation. Now, from that Euler equation, again, once you start putting in constraints, again, if you have algebraic constraints, the general way to do that is to consider the Lagrange multipliers. Now, the Lagrange multipliers have their usefulness, and we'll talk more about this when we do the mechanics. So we talk about Lagrange mechanics. So in that case, as I kind of mentioned, the Lagrange multipliers give us information about forces, mostly constraint forces, as opposed to if I wanted to, by knowing the algebraic expressions, I can simply eradicate one uh, variable for another variable because I know how they relate to each other. So in that case, I could rewrite my entire expression in terms of the one variable instead of both variables. Now, the problem with that, or I shouldn't say the problem, but the downside of that is it doesn't give me any information about these constraint forces. So if I want to know about constraint forces explicitly, I would have to then use the Lagrange multipliers. But that's it. So this is the end of this chapter. So next chapter, we're going to start moving into Lagrangian mechanics. So talk about Hamilton's principle and all these different things. So basically what that does is it's going to use all these ideas from the calculus of variations to allow us then to now be able to solve physical systems, where in this case, we're talking about mechanic systems. So we'll go through all that, basically just kind of do some modifications to everything, but they'll still satisfy this Euler equation, but it's now going to be known as the Euler-Lagrange equation. So anyways, yeah, so that's it. I will see everybody on Monday.